Next up, let's take a look at the constant multiple rule. This is for functions multiplied by a constant value. We're going to observe that if f of x equals c times g of x, so c is some constant number. Hey, that's convenient. It's called the constant multiple rule, and we're dealing with constants that are multiplying by our function. Cool. So if f of x equals c times g of x for some differentiable function, g of x, so g of x must be differentiable, and c is an element of the real, then we observe that f prime x equals c times g prime x. In Leibniz notation, for some constant, c is an element of the real, ddx of cy is equal to c dy dx. Note, you will see proof of this using first principles in a video, so we have another video on bright space that will prove this. All right, let's work through a few examples though. So we're not going to prove it here. We're going to do that in that other video link. We are just going to practice using it for now. And we are asked to determine f prime x for the following functions. In the first case, we are looking at f of x equals 3x squared, or we could represent that as y equals 3x squared. And how are we going to do this? Well, let's work through our notation. We've seen that we can kind of move the constant in front of our derivative or our differentiation. So let's write this. dy dx is equal to 3 dy dx x squared. So the constant gets pulled out front, and then I'm finding the derivative of the rest of my expression. So I'm going to have dy dx is equal to 3 times, and let's use our power rule, bring that 2 down, x to the power of 1, which is just x. And now I can simplify. Dy dx is equal to 6x. And you don't strictly need to use this notation. I could have left f prime of x equals, well, this is where it gets a little tricky, because then it's like, well, f prime of x equals 3 times the derivative of x squared. And if I want to just write it directly, I can, but the dy dx notation lets us kind of split it into chunks and makes our life a little bit easier. But ultimately, I can't just write f prime of x equals like that. That's fine. All right, in our next case, I'm dealing with an exponent function, so I don't need to use my power rule here. Do not use power rule. Because what do I know about the exponential function? Well, I know that it's its own derivative, and I know that if it's multiplied by some constant value, the derivative is just still the exact same function. So I'm going to have f prime of x is equal to negative 2 e to the power of x. No change necessary there. Let's take a look at cf of x equals 5 times sine x. Once again, f prime x, that 5 is going to remain. And I'm just finding the derivative of this chunk right here. The derivative of sine x is cosine x, as you hopefully recall. And for d, f of x equals 4 over x to the power of 3. We can rewrite this so everything's on top in the numerator. All right, now it's a little easier to work with. It's just another power function. So my derivative, the constant value is going to remain. I need to bring down my exponent so that it becomes a constant as well. So negative 3 comes down in front. X, and subtract 1 from our exponent. Negative 3 minus 1 becomes minus 4. We can simplify and tidy this up a little bit. 4 times negative 3 is negative 12. X to the negative 4. And let's have a positive exponent. Negative 12 over x to the power of 4, or just negative 12 over x to the power of 4. All right, that looks pretty good to me. Let's zoom out for a moment to get a snapshot of the whole thing. And then we'll continue. All right, the sum rule for sums and differences of functions. Because remember, when we find the difference, you're just adding the negative. So subtraction is basically just fancy addition. The sum rule for sums and differences of functions. if f of x is equal to some functions that are being summed, f of x equals p of x plus q of x for some differentiable functions, so p of x and q of x must be differentiable, then the derivative is just equal to the sum of the derivatives of the other functions. So nothing too terribly scary or hard to memorize here. And also, if we're subtracting, if f of x equals p of x minus q of x for some differentiable functions p of x and q of x, then f prime x equals p prime x minus q prime x. In our derivative, or sorry, in Leibniz notation, d dx of u plus v, where u and v represent our different functions, du dx plus dv dx. And if we're subtracting, d dx of u minus v is du dx minus dv dx. And once again, we're not going to prove this here. We're just going to observe the patterns. And there is another video that we'll see linked that will explain that. Let's work through a few examples. Let's try actually applying these rules to some functions. Determine f prime of x for the following functions. And how are we going to think about this? Basically, we want to think about it piece by piece. So when I see questions like this, we're going to think piece by piece. So I can do each part individually and then add them together or subtract them or whatever is required. So piece by piece or term by term. And we could also extend this and consider how this might apply to the derivative of a piecewise function. And let's start with that example first, actually. So if f of x is equal to 2x if x is less than 0, and x squared if x is greater than or equal to 0, then we'll have our derivatives f prime of x, f prime of x is equal to 2 if x is less than 0, and 2x if x is greater than or equal to 0. And what is that going to look like? Well, let's take a look. xy. So 2x if x is greater than 0. If x is less than 0. So just going to be a linear function with a slope of 2 until we get to 0, and then it becomes a quadratic. So something like that. And let's draw our derivative function. So if it's less than 2, it has a value, or if x is less than 0, it has a value of 2. And after that, it has a value of 2x. So that's kind of cool. And so we can see right away that our linear function had a constant derivative, and our quadratic function had a linear derivative. And we should label that. This is our f prime of x. And this was our f of x. All right, let's take a look at some power functions as well. In our first question here, we are looking at f of x equals x cubed plus x squared plus 4x plus 7. And remember, we're just going to take the derivative of each piece and then add them together. So I am going to have f prime of x is equal to the derivative of x cubed Actually, we'll just do it this way. D dx. So we're going to find the derivative of that, 3x squared. So 3x squared plus our next derivative, d dx of x squared is equal to 2x to the power of 1. I don't need to rewrite that power of 1, so I'm just going to write 2x. And d dx of 4x, well, that's just going to be 4. And what's the derivative of a constant? Well, let's think about it this way. 7 to the power of 1 equals 1 times 7 to the power of 0. Anything to the power of 0 is 1, so 1 times 1. So 1 sorry, that's not right. We can't do that because there is no variable. So the derivative of a constant value is just 0. So if we had, our constant value, what's the slope of that line? Well, it's going to be 0. We've seen that already. So the derivative of 7 is just 0. So plus 0. So I don't need to write that. So I can just write f prime of x is equal to 3x squared plus 2x plus 4. Let's do our next one. I'm not going to show as much work this time. We're beginning to see the patterns. F prime x equals, bring that 4 down and multiply by anything that's already there. So 4 times 5 is 20x, and reduce our exponent by 1 to the power of 3. Minus, that 2 comes down and says hello to the 7. We're going to have 14x to the power of 1. I don't need to write the 1, so just to the power of x. Or just to the power of 1, so just times x. All right, and be careful here. We have an exponent function, so don't try to apply power rule there. Just use what we already know. F prime x equals 2 says hello to 3. 6x to the power of 1. Don't need to write the 1. And we have an exponential function with a base e, so it's not going to change. It's its own derivative, so minus 2 e to the power of x. And sine prime is cos, and negative cos prime is sine, or cos prime is negative sine. So the derivative of positive cosine x is going to be negative sine x. Not too bad. And finally, we got a little bit more flavor for this last one, but we'll still approach it one piece at a time. Anytime you see a question that you're not too sure of or looks scary, just try to break it down into pieces that look familiar, or try to think about the tools we already have to deal with similar problems, or just try rewriting it in a different form. I know I'm using power rule, so I should maybe try to express these things as powers. So we're going to rewrite this as 4x square root means to the power of half, minus 3, and x in the numerator is the same as x in the denominator is same as x in the numerator with a negative exponent. That looks a little bit easier to work with now. So f prime of x is equal to, that half is going to come down and say hello to the 4. So let's show our steps here. 4 times half, x to the half, minus 1, minus 3 times negative 1, x to the negative 1, minus 1. And so we're going to get f prime of x is equal to 2x to the negative half, plus 3x to the negative 2, or we can rewrite that with usually with positive exponents, and square root signs is preferred. So we're going to have 2 over, that's our negative, our half is the root x, plus 3 over, and the negative brings it down, and it's still squared. All right, once again, that wasn't too bad. And that brings us to the end of our derivative rules that we're going to look at. And so we had a chance to look at in our previous videos as well. So we've learned about, this doesn't scroll smoothly for sometimes. Scroll smoothly sometimes, I don't know why. All right. So we saw that we don't need to use the first principles every time. We can take some shortcuts. So we saw our constant rule. So the derivative of a constant function is equal to 0. We saw the power rule. So when we're dealing with polynomials or just any variable with an exponent on it, we can bring the value of the exponent down in front as a constant multiplier for our variable x, and then subtract 1 from our exponent. We saw the constant multiple rule. So if f of x equals c times g of x, then f prime of x equals c times g prime of x. So the constant kind of gets pulled off to the side. We find the derivative Then we put the constant back in. And if we are adding, so summing or subtracting or finding the difference of two functions, then I am just going ahead and finding the sum of their derivatives or the difference of their derivatives. And once again, this assumes that my sub functions, or my p of x and my q of x or whatever, are also differentiable. And then we work through a couple examples. So as you can see, this is going to make our life a lot easier. I can find the derivative in like a single step. So like right here, I didn't even show any work. I went straight from the function with multiple terms to its derivative without any work. I didn't need to use first principles. I didn't need to find the limit as h approaches 0 of f of x plus h and then put it into all the terms and then fill up like half a page with writing. So that was important to get foundational knowledge and understand how and why this works. But now that we have done that and observed patterns, now we can go ahead and start using the shortcuts and making our life a lot easier.